Okay, perfect. So my goal is to show you the key feature of Yugabyte. And of course, there are many features. We are Postgres compatible. The goal is not to show you all the features that we have in Postgres, just we are compatible. The key feature is the scalability that we add on it. So I'm Franck Pachot. I'm developer advocate at Yugabyte for about 2 years. Developer advocate means that I talk about Yugabyte at conferences. I blog a lot to help users depending on the questions, but also I'm very interested by any feedback, the questions about it, people who try it, what works, what doesn't work. I report to the CTO and I work with the product management team. So we are fully open source. We build a community also to get feedback and improve the product. We cannot build a database without knowing how it is used and what is useful or not in the database. So I'm speaking English with a French accent. If you can ask anything, you can ask for translations. If something is not clear, do not hesitate. We are there for sharing. And I will go quickly on the features and do a demo, which will also be the occasion to ask questions. Do not hesitate to interrupt me at any point. Basically, Yugabyte, the main key features, the main differentiators with other databases. First, it is a distributed SQL database, which means that it can scale out. Not a monolithic database where you have only one server, and if the server is down, your application is down. We are distributed. And distributed SQL is more than just having replicas. All the SQL features are distributed. Means that your tables, your indexes can be on many servers, nodes, availability zones, regions in the cloud, data center. You should see one database, one SQL database, and have foreign keys, global indexes, all that over that. That's the difference between distributed SQL databases and what is called sometimes new SQL, those monolithic databases that has some scalability, but not for the full features. Yugabyte is Postgres compatible at the highest possible level for a distributed database, simply because we just reuse Postgres. Postgres is open source. It's a very popular open source database used a lot in enterprises for OLTP. And rather than reinventing all SQL features, we just took Postgres and plugged that onto a distributed storage. So you should have good compatibility by taking just your application and changing the connection string and connecting to any node of a Yugabyte cluster. And then it is also fully open source. That's really the idea, also to give freedom. Building a new database is not easy, but for users, it's also not easy to move the core applications to a new database. You need to trust it. And one way to get trust is to open source, be open, and give freedom. So just an history. It has started in 2016. The founders have been working at many database vendors like Oracle, monolithic databases, but also they have built Cassandra and Database. And that's the idea. You want the same scalability as those NoSQL databases, but with all the features of distributed systems. And basically, the architecture is based on Google Spanner. Google was the first one realizing that with NoSQL, yeah, that's cool, you can scale, but you miss a lot of features. If the database doesn't provide integrity constraints, foreign keys, stored procedures, all the things that has been added to SQL database. If you don't have that in the database, you can work around it with more code in your application. But your goal as developers is to have the business logic in the application code, not all the code to manage replication, consistency, all that. That's the job of the database. People realize that when using NoSQL databases, they were building database feature in the application, and that's not the goal. You develop an application, you don't develop another database. So we develop a database that provides all feature. Google Spanner started with this idea. Then CockroachDB, TIDB did something also with some Postgres compatibility, some MySQL compatibility. And Yugabyte really, the idea was that the future is to have all SQL features, because if we needed them in all databases until now, we will need them in the future. So rather than reinventing all features, re-implementing them, just using Postgres and plug it in, of course, optimizing a lot of things. It's just not just plugging, but that's the idea. So basically, distributed, you can scale out horizontally, multiple nodes. The database runs on multiple nodes. Why Postgres compatible? For the familiarity. You don't need, as a developer, to learn a new database, new syntax, new isolation level, behaviors. What you know about Postgres, you can use it on Yugabyte. Of course, for operation, for the infrastructure, it is different, but from the application, you can use the same knowledge. If you have questions about how to do this in SQL, if you search on Stack Overflow about how to do this in Yugabyte, you will not have a lot of answers because Yugabyte is new. If you search how to do it in Postgres, you will have your answers, and they will work on Yugabyte because it is compatible. And I mentioned open source for the freedom that it gives. So, yeah.
キーフューチャーというところで、その分散データベース、分散スケールデータベースというところですね。で、あと、ポストベース互換という、あと、オープンソースであるところが、まず一番のポイントとして話しております。なので、ちょっとこの話も出てきますけれど、分散スケールということで、スケールアウトするところがポイントになる。あと、ポストベース互換というところでは、その、互換性が強いっていうのは、思ってた、その、ユーザーさんでちょっと、私のあるのは、人気の OLTP のデータベース機能を追求していきたい。オープンソースというところで、ゼロから何かするというよりかも、今回のようにコミュニティの皆さんの力を得ながら、新しいデータベースを作っていく。で、スタックオープンワークフローとかみたいなタイプにいて、Yugabyteと違うと、まだまだ情報は少ないと思うんですけど、これ互換性が高いところから、ポストベースと同じようなことができるときたいというのが非常に大きいと思うので、ぜひ皆さん使っていただきたいと思います。あとは、スパナークローンみたいな調査され方もしますけれど、やはりただ分散させるだけではなくて、きちんとデータベースとしての機能というのを追求していくと。で、我々、さっきも、フランク言ってましたけど、ポストベースのコードを、再利用、うまく使っていくことによって、ゼロから何か新しい機能を作る、かつ、何かが主要な機能が書ける、例えば、プロシージャーとか、ポリティとか、そういった機能が書けることなく、そのままデータベースとして使えるっていう、分散でスケールで申し上げてますけど、データベースそのものとして使っていただけるようなことを目指しています。はい。
So basically, the features that you want in a database without thinking what database provides, you want architectural resilience. That means that if something fails, it just continues, and not with added product on top of it that adds complexity. Architectural means the database is built with resilience. And if you scale out, if one node is down, everything continues on the other nodes. Horizontal scaling for performance also, but for high availability. And today also people want geo distribution, not for every use case, not for every companies, but many companies have users all around the world, and they need to put data in different regions for legal reasons, because you are required that European citizens are stored in a physical location in Europe, or simply for latency reason. Makes no sense that a user that is in US connects to a data center in Japan. even if the company is from Japan. And you still want ACID transactions, so the consistency, the atomicity. Basically, what SQL databases provide with ACID transaction is that if you test your application with a single user test, it will work even at race condition when many people will touch the same data. The database will manage what can be done at the same time or must be serialized, but you don't have to do that because testing an application is one thing, testing all race conditions when you have thousands of users doing different things, that's more difficult. So, and all SQL features, because even if you don't build all your application in stored procedures, at some point you will need a trigger, you will need a stored procedure. And basically that, I mean, that's what we want for a database. With the monolithic SQL databases, we had those ACID and SQL features. With no SQL, when we wanted to scale to go geo-distributed, we had the distribution, but now we just want both because no SQL databases, Cassandra, you will not have the ACID transaction, the SQL features, and traditional SQL databases, you will not have the scalability. So here, the idea of distributed SQL in general is to provide all that because today the technology allows it. Technology for database, but also technology like the cloud. Today, it is easy to provision servers on multiple regions. It was more difficult, not a priority before, because you needed to build a data center on your own, and it was more difficult. But today, we just can't do that. And yeah, basically, the architecture, Yugabyte started by building a distributed data store, transactional, to allow fully ACID transactions. And then on top of it, plugging the SQL layer by using Postgres. And not only the SQL layer, Yugabyte can also have a Cassandra compatible endpoint. The idea is that also today people build microservices, and maybe for some use cases, they want to use Cassandra. For some use cases, they want to use Postgres, but they don't want to manage plenty of them. So the idea is that on the lower layer, we store and we manage transactions. So we even have Cassandra API with transactional behavior, but at least all can be on the same database. And with traditional databases, you want multiple databases because if one fails, you don't want to fail all applications. But here, because the database is resilient, you can build multiple microservices on it. And deploying that everywhere means behind the distributed storage, there are multiple nodes that can be containers, can be VMs, can be in the same data center or different data center in one cloud vendor or multiple cloud vendor because you want to move from one cloud vendor to the other. Okay, now I will explain quickly how it is distributed, but the goal is to tell more around the demo. So basically, to distribute data, you need to split at least the big tables. Splitting them, kind of partitioning, but I will change the term. I will explain why. A table has rows, and what we want is assign rows to different shards that we call tablets. Can be on a hash value on the primary key, can be on a range value on an index. You choose, but once you decide how it will be split, then the database will manage that. Realize that maybe one tablet is too big, split it into two, or one table has all its tablets on the same server, move that away. So the sharding breaks the tables into multiple pieces. Tables and indexes, they are the same for the storage. You store rows or you store index entries. One row goes to exactly one tablet. It is distributed because other rows will go to another tablet that can be on another server. But of course, we cannot do magic. If all your transactions are updating the same row, you will not be scalable. So you need to think about the design, maybe multiple rows, multiple buckets, and you choose on range or hash. Basically, when you apply a hash function, this distributes better the data, but you can do only point queries. Query with where clause, colon, equal something. If you have colon between two values or higher than one value, then you cannot apply a hash function. So for those, you decide range sharding on range of values. And all that is automatic. And let's call that sharding and not partitioning, because in NoSQL databases, it's called partitioning. But here we have also SQL. And in SQL, you can also partition. But that has another goal. This one, sharding, is there to distribute data. On top of it, we can partition it. For example, if you want to put some information in a specific region, probably you will partition your table to have one partition on in Europe, for example, one partition in another place, depending on the data there. And basically, sharding to tablet is there to distribute to multiple nodes, but also to replicate them. Because the goal is to be resilient. You don't want only to distribute, you want to have multiple replicas so that if one is down, the other has the data without any data loss. So for that, each tablet is a Raft group. Raft is an algorithm that ensures that a change is propagated to replicas and ensures that you can have consistency, because one of the replica will be the reference, the leader for read and writes. So you are consistent, but the followers will be updated. But what you don't want also, you don't want to wait for all other nodes to acknowledge. So it waits for the quorum, the majority of other nodes. Basically, you write to a follower, it sends the write to the others, it waits for the acknowledge for one of the two followers if you have a replication factor of 3, and then it can acknowledge the write. The other follower may lag a bit, but if the leader is down for any reason, any failure, then the two followers, if they talk to each other, they can know which one has the latest value, and they know that it can elect a new leader. But we will say that in the demo. Basically, that's the algorithm it is based on to replicate while keeping the best possible performance. Of course, you add latency when you replicate synchronously, but if you don't want data loss on recovery, you need some synchronous replication. So each tablet is a Raft group, right? Go to the leader, replicate it to the follower. It waits for the quorum. Consistent reads, and by default in SQL, you want consistent reads. They go to the leader because there they are sure to find the latest value without asking to the other. You don't want the latency asking to multiple followers, for example, like Cassandra can do. You have also the possibility, if you accept a little staleness, to read from the follower to reduce the latency. And because if you are running a report, you probably don't really need the latest changes. So there are many features that are there to reduce the latency. In case of failure, a new leader is elected from the quorum. Quorum is the majority of nodes. The idea of quorum is that we want only one leader, because if the application, if the users start to write on two places without knowing about each other, you will just corrupt your database. When it's back, you will have changes and you don't know how to order them to really have the latest one. So when you have a quorum, means that you deploy on 3 servers or more, or 3 availability zones, or 3 regions. But if one is down, the 2 others know that they can continue, and the one that is alone cannot take any write. And about the storage, it's also different from traditional databases. more like the NoSQL databases, and for modern storage, LSM-Tree rather than heap tables and B-tree. We can go a bit further later if you want. Basically, didn't reinvent everything from scratch. Each tablet replica is a small RocksDB database with a lot of evolution on it to make it efficient for this case, but basically that's the idea. So quickly, those two layers are seen like each server has a part of compute and a part of storage. The compute is the Postgres code running. So you connect to any node, and then you have a Postgres backend. It parses your query, it builds the execution plan, executes it. But when it has to read and write, then it talks to the other to get the data from there. Basically, the stateless part of Postgres on top of a distributed key value storage. The internal API between them is kind of a key value. And I will go directly to a demo, and we may come back to the slides later. Basically, so you will have the slides. Basically, I will run a small cluster on my laptop with Docker. So let me check. I have Docker desktop on my laptop, and here is a terminal where I will first create a network. Of course, the container needs to be able to talk together. It's a distributed database. It was already created, but it is there. Now I'll start the first node. So the Docker command, the name of the first node will be YB0. I will add YB1, YB2, basically. So the image I'm using there. And basically, the command is YugabyteDB start, the Yugabyte daemon starting a new instance, a new node with this name, YB0. And that's mostly all. I already have one running. And you see that I tunneled 2 ports. 5433 is the Postgres endpoint where you can connect as you connect to Postgres. The other 7000 is a small web console, and we will look at it because that will help to explain the concepts. Basically, the list of tablet servers, so the server that holds data and where you can also connect to, I have only one for the moment, and I have no data. So I will start another node. I have the command here, and basically it's the same command, except it's YB1 instead of YB0. And I add a join to join the other one. Because if I don't do that, I will start another single node cluster. Here I want to have a new node that joins the cluster. So of course, the UI from the first one can see it. If I refresh, I have 2 nodes. With 2 nodes, you cannot do replication. You cannot do sync replication with a guarantee of no split brain because you don't have a quorum. So replication factor is still 1. I'm not yet resilient to 1 node failure. When I start with 3 nodes, so let's start the third one, YB2, then I will be able to have a quorum. So starting with 3 nodes, I can be replication factor 3, which means 3 replicas on 3 nodes, which means that if one is down, there is still a quorum for all tablets in one of the other nodes, and then the application just continues.
を使って、スタンプスを一つずつ立ち上げておく。最初、どっかのネットワークにして、それで説明にしていくつかお見せしている、ここで見せている7000番のポート管理の画面を、提供している UI のところがあって、そことあと743か5433という、通常のポストグレス543と、今までの543それですね。YSU に関すると、それから教えていただきたいと思います。追加で、いくつかのコマンドを、プラジルのコマンドを言ってますけど、ポストネーム、ちょっとずつ変えて、クラスターとして3ノードが上がっているような状態にしています。これは全部オープンソースのもので見ておりますので、また資料を公開しますので、皆さんぜひ、戻ってください。あるいは今、このように見ていただきたいなと思います。
So now I have 3 nodes. So if I refresh there, I have replication factor 3 tablet server. I can start to connect, create some data. They will be protected. So to connect, because it is Postgres compatible, I just use PSQL, the Postgres client. I connect to the node of tunneled to the first node, the YB01. So I'm connected to YB0. We have a view that shows all other servers there. But basically, I can do everything that I can do in Postgres, like, so I create an extension. We do not support all extensions because we have a different storage. So the Postgres extension that do something at storage level do not apply there. But here I'm using PG crypto that just adds some functions. For example, because I will generate some UIDs. And yeah, that's worked because that's only at the SQL part of Postgres.
今お見せしているところで、さっきの右サーバー、プラスのサーバー、うちの機能としてプラスの状況が見えるのでするんですけど、基本的にはポストグレス、先ほどから申し上げているコンテンツリーとエクステンションも可能な限り分かるかもしれないですけど、ストレージ周りを独自の実装しますので、ストレージ周りにあまり関係しないようなことです。うちではエクステンションの使いすれば BGP という皆さんが何か知れるものを使える。
So I insert a row and I also insert the value of listen address so that I know where the row comes from. If I select, I have one row, of course. And then I select another node, so the other port that I have tunneled, and I insert a row there. Of course, you see that as one database, you connected from multiple places, but you inserted into the same table. That's the main idea of distributed SQL. I'm just inserting a new row. And I will run this insert in a loop. So using Postgres syntax. Every half second, it inserts a value. Maybe I will do it more frequently to see more activity. So now the application is running. If I go to my small web console there, and I refresh, I can see that I start to have some data, but more important, you see the read and write operations. those are the operations received by the tablet servers. So it's not the number of SQL statements. The SQL has already been transformed to an execution plan. It's really the read and write operation, like write for this key, this new value for this column, or this index entry. And here I run inserts from one session connected to YB2, but all my cluster is active. You see the number of operations per second is there. Because I'm inserting generated UIDs, they are hashed to different values that goes to different tablets that have their leader on different nodes. So this is how it is distributed. I have 3 servers running even if I'm connected to only one.
この安心しているときは、特定のノードをさっきもYB2、これで一番下のやつ、コネクトしてインサートしてるんですけれど、ご覧いただけるように、インサートしているライトのオペレーションが1個のノードでやってすでに後にされているんですが、さっきも説明したように、タブレットっていう概念があって、タブレットはそれぞれのノードに分散されているということがあって、特定のノードだけにライトが発生するのではないか、分散されている。かつSQL の、オペレーションを行っているわけですけど、すべてはその下のストレージのレイヤーに、実際のデータソースが生まれているので、実際に分散しているところというものを見ていただくんじゃないかと思います。
And if you want to understand a bit more how it is distributed, there is a view on the tables there. So that's my demo table. You see that it has 3 replicas, and I have something to make the screen a bit easier to read. So here I have 3 tablets. And the first tablet holds the hashed value from AAA to FFFF. This other tablet holds all the other values. So this is how it is distributed. And you can see that each tablet has a leader and 2 followers. And of course, not on the same node because you want to be resilient. So you can see that this one has a leader on YB0, this one leader on YB2, this one leader on YB1. This is why you see the write operations that are distributed because they have leaders everywhere and followers on the others.
ボードでパーティションというか、シャーリングっていうのをした方がいいように、実践データがシャーロされている。それのハッシュがどういう範囲で決められているかというのをここで見ていただきます。リーダーというのは基本的には12をメインに使われているので、見ていただくと YB0、YB2、YB1 できれいに分析されていて、かつフォロワーもそれに対して分析されているのが出ている。それがさっきのタイプがきれいに分析していたところの理由です。
So basically, the only thing I did was defining a primary key. 3 tablets, because that's the default. I had 3 servers when it is created. Of course, when there will be more data, the tablets will be split. I think that if I refresh to show all the column, you see a split depth. When it will be automatically split, you will see that. Okay, now, so Yugabyte key feature, the first one is the elasticity. When you are on the cloud, it's quite easy to add new nodes. Like here on Docker, it's quite easy to add new containers. And you want the data to be rebalanced. So I'm just opening a new terminal there to run this command that will start 3 more nodes. So it starts will be 3, 4, and 5. And I will refresh that. Yeah. And you can see that just after that, we start to have the new nodes used, YB3, YB4, as followers. Now I have 4, because to move a follower to a new node, it starts by building a new replica, and then can remove the other one, as it is fully online. So now if I refresh, probably I will have one less.
で、一瞬フォロワーが増えて見ていただけたと思うんですけど、ちょうど増えたことのバランシングを、動的に行っていて、その瞬間、まだバランシングしてたタイミングだったので、フォロワーが形になって見えてた形になって、今、フランクリフレッシュした状態ですと、きれいにまたフォロワーが新しく追加されたものに分散されているというところが見ていただけるかと思います。
And the application was just continuing, because at some point it has even elected a new leader on the new node, but that doesn't interrupt anything. At least if there is an ongoing write, the database may redo it on the other, but without giving any error message to the application. So 2 things were rebalanced there. First, the data by creating new followers on the new node. And then another thing must be balanced. The leader takes reads and writes. So this one uses more memory than the followers and more CPU. So you also want the leaders to be balanced. And that's what the database does automatically. First, detecting that some nodes do not have enough tablets to be balanced. So create new followers there, and then elect some leaders there. So basically, that's the elasticity, because of course you can use it on premises, but if you go to the cloud, you will not provision your machines in the same way as you do on premises. You will be cost efficient in the cloud if you can stop some servers when you don't have a lot of activity, and start new one when you start to have more activity. If you provision the full capacity the whole year, your cloud vendor will be happy, but probably not your financial director. So if you move to the cloud, you want this elasticity. Also on premises, if you deploy on container, on Kubernetes, you want that. This is what we call cloud native. I did nothing at database level. I scaled with cloud command, adding a container, scaling a Kubernetes stateful set, adding a VM, and the database handles that. I didn't have to think about rebalancing data, enabling more replicas, moving replicas, and all that. Do you have any questions for the moment?
Sorry. さっきノードを追加したことによってリバランスされてましたけど、リバランスには2つあるというふうにフランク言ってました。1つはデータを分散するところですね。フォロワーというふうに書いてありましたけど、基本的には追加されたノード十分なデータが分散されていないようであれば、フォロワーという形でデータを分散する。あともう一つはリーダー読み書きを中心に行う部分というのが、基本的にコンピュータリソースを消費しがちなので、それをまた配分するというところで、この2つのリバランスが行われます。で基本的にはこういった機能を持つことによって、もちろん皆さん、オンプレミスで使っている環境もある、場合によってはクラウドの環境もあると思うので、そういった環境のリソースをうまく使う、エラスティックっていう話をしてましたけど、柔軟にその構成ができる、かつ使った分を効率よくうまく活用するための仕組みっていうのが、皆さんの手を渡らせること動的にできるっていうところは、うまくクラウドを活用するっていう意味でも、クラウドネイティブができるんじゃないかっていうコメントをしておりました。ごめんなさい。あと質問があればぜひお願いいたします。
If you have questions about this point about elasticity, I'm just showing that if I refresh, so now I have 6 nodes, and I have activity on all of them, maybe not all of them because I have small tables, small number of tablets, but you see write activity on mostly all of them. This is because the leaders have been rebalanced. Yeah.
So when we created the 3 first nodes, so like 3 tablets created, right?
Yeah.
But then when we added another 3 nodes, new 3 tablets were not created, but these 3 tablets choose just the new leaders. Why that? Why?
Yeah, the idea of splitting is being able to distribute and keeping the size of each tablet in a manageable size. The goal is not to follow the number of nodes, because with this elasticity, 3 nodes for a replication factor 3 is the minimum, but you will have a copy of the whole database on each node. And probably you don't run that. Here I have 6 nodes, but I don't run a copy of each. So the same tablets were just moved. They will be split only if they grow in size.
So basically, when it's growing in size, and we already have 6 nodes, they might choose the new.
Yeah. Actually, the auto split algorithm has 2 phases. One that is more aggressive in splitting to distribute. So if you start with a table with only 1 tablet, you start to load data. As soon as it reaches 500 megabytes, it will split it. And that phase until you have 8 tablets. Those are parameters, just works. Of course, we can change it. So the goal is aggressively split quickly to get 8 tablets per server. And then it switches to a mode where you don't need this aggressive splitting, you just need to split when it is too big, and then it will split when it reaches 10 gigabytes. For 2 reasons. First, behind there is a YugabyteDB that's very efficient for 10 gigabytes. It would not be efficient for 1 terabyte. The other reason is that all this elasticity may have to move some data, initiate some replicas. So having small chunks, you don't want to do it with small blocks, but at least small chunks that are easy to move and all that. So then the goal is 10 gigabytes. But you can have full control. Usually the auto split is sufficient. The table grow and then a split happen. It doesn't stop anything. Of course, if you create a table and you know that you will load a lot of data, you can pre-split it rather than the default that is 1 on each server. Also depend on the number of tables you have. We have users using Yugabyte with kind of microservices, and there you see a few big tables. And there are people just taking a Postgres application or an Oracle application and move it to Yugabyte. And there you may see schemas with hundreds, even thousands of tables. You don't want to distribute all them to too many tablets. So at that point, you can also collocate some tables within the same tablet. Basically, an OLTP application has 100 of small reference tables. You just want to get them together, because you don't need to create more tablets, but also if they are collocated, when if they check the foreign key, for example, between one to the other, it will be a single node call rather than a network call. So you can collocate many small tables, and the 5 tables that increase are sharded, but they will be split automatically. And when it is split, behind it's stored in LSM-Tree SST files, so that's the YugabyteDB storage, and there is some compaction in the background. Basically, when it is split, it takes a copy, just discard half of it on each of them, but you reclaim the space when the compaction happens on it, removing it, so background job. But the compaction is very different from the Postgres vacuum, for example. The Postgres vacuum locks a lot of things, brings a lot of problem. Compaction is really at lower level.
質問としていただいたのが、ちょっと私の理解だとすると、ノードを追加したのに、 ノードが追加にして、フォロワーが分散されるのは分かったんだけど、なんでタブレットが3のままで、タブレットがもっとコピーして分散されないのかみたいな質問だったと思います。なので、おそらくイメージとしては、データ分布でデータの方が増えるから、タブレットの方も増えている質問じゃなかったと思う、だったかなと思います。で、一応答えとしては、基本的にタブレットの数っていうのは、増えない。で、もともと先ほど、フランクが説明したように、そのレプリケーションファクターというものを3って決めてあるので、基本的には3つのコピーを取る形になるので、ここにあるように、リーダーに対してフォロワーが2つという、この3つのコピーを持つ状態というのは変わりませんと。じゃあどうやったらタブレットが増えるのかっていうと、データが増えてきたタイミングで、このタブレットを増やす。これは皆さんの方で手動でやるか、もしくはオートスプリットという機能が最近追加されたので、ある敷地を超えたときに、自動的にスプリットされるようなことが実現されます。で、それが敷地、最初は100メガって言ってたかな。100メガが最初で、あともう少し大きくなると10ギガまでっていうところがあって、あまりデータが大きすぎると今度は分散の効率が良くなくなるので、オートスプリットをするということが必要になってきます。ちょっと会場からの質問だったので、ズームの方々に聞こえてなかったかもしれないので、ちょっと補足させていただきました。
So second key feature, this was about elasticity, but you also want to be resilient. So for example, you see that this one has a leader on, or let's take the last one. This one has a leader on YB4. If YB4 is down, you cannot write to this leader. So one leader will be elected on the other to continue. So let's take down YB4. I choose YB4 to show explicitly when there is a leader, because that's the worst case.
ちょっとリーダーのノード一つを YB4 というやつを殺してくる。これは最後のタブレットのリーダーだったやつですね。
And we look at the application. So first, the decision to elect to vote for a new leader, we wait for 3 seconds for that. Just not to have new leader election if there is just a small network issue. And then you have the TCP/IP timeout for the connection that we're doing a write. So here, because I had a session always doing writes, at some point, even when the new leader is available after 3 seconds, at some point, it was trying to reach the YB4 that is down, and then the TCP/IP timeout that we have set to 15 seconds, it will wait for that before going to another. Another session could already work on it. It's just because this one was already waiting, and you have seen 50 seconds and the application continues. So 15 seconds, it's not a downtime. 15 seconds, it's just seen as a performance issue. You probably don't have an application timeout for 15 seconds, so it's just slow. And this because one node is down, or because one data center is burning. It's quite the same. And to be clear, when you have many nodes here, I have only 3, and I have a session touching all of them. If you have many nodes, let's say 10, 100, if one is down, so first you have distributed the connections. So you will have 10% of, I said one with 100 of nodes. So 1% of the connection will get an error. If they are connected to a node that is down, they get an error, connection timeout, then the connection pool reconnects. And that's only for 1% of them if you have 100 of servers. If a session was connected to another and currently was writing to this one, they will wait for the TCP/IP timeout, 15 seconds, and everything continues. Most of the other sessions just continue because they were not writing at this failure time to a tablet that was on this node and they were not connected. So what we see that is the maximum time, the 15 seconds.
今の一つのことしたら少し手がけど、もう ノードとして、リーダーのセレクションで、別のリーダーがしたときに、大体3秒ぐらい、レコードで3秒、3秒ぐらい足を失礼します。で、CPU のタイムアウト4秒ぐらいが想定されるので、その3か所15、18秒待てば、またコネクションとして復活する。これは、切断というかも、PCB として遅いという状況になっているだけで、アプリとしてパフォーマンス下がっているんですけど、そのまま続いていることができる。前に実際に接続してからこの自体が欲しいという可能性はありますので、その場合は、コネクションタイムアウトになっているますけど、それも全体のうちの、数パーセントになっている、100ぐらいの場合で、ノードの数なんですけど、50%すると、それだけがタイムアウトして、する必要があるので、そういう意味では、コミュニケーション継続的にデータベースに接していくというのが一つの、運用性を維持できることです。
The node I've taken down was YB4, I think. So you can still see that you have some followers there, because usually those kind of failures are short time. So by default, that's again a parameter. By default, the other replicas keep 15 minutes of changes in their log, so that if YB4 comes back, it will just catch up the latest changes and can continue. After 15 minutes, we consider that this node is really down, and we will not continue keeping all the logs for him. So after 15 minutes, but I think we will not see that. After 15 minutes, this one will be removed from the Raft group. Another one will be created on one of the remaining nodes, and maybe a leader election. So this still works when one of the follower is down, because you have the quorum. So you write to the leader, it sends to both of them, cannot send to, it's not received by YB4, but YB5, receive, acknowledge, and that's okay. You just cannot have another failure. For example, here I have YB4 down. If YB5 is down, you can do it.
なので、さっき落とした後の4がまだ残っているのは、一応クラスターの状態としては、まだそのメンバーとして残しているんですけど、一応タイムアウトとして15分経つと、クラスターからメンバーとして削除をして、新しいメンバーを追加することになるので、15分は、例えばそのネットワークダウンとか何かあった可能性があるので、一応その余裕を見て15分という時間を取っている形になります。
The database cannot accept writes that are not protected. So here, replication factor of 3 and 2 failures, the database stopped until it is back. If I take it back, this will continue.
今、もう一つのノードを落としたことによって、データベース自体は今、受付ができない状況、特にライトについては受付ができない状況になっています。
Let's take 4 back.
今、ノード4ですね。最初に落とした方のノード今、また。
I'm not sure about the timeout there, but we will see. But basically, with replication factor 3, where is it? Replication factor 3, you are resilient to one failure. Here, those are nodes because I didn't assign the node to specific zones. If you see that each node there have a tag for the cloud region zone. They are all in the same. If you deploy in 3 availability zones, when you start the tablet server, you will tell them you are in zone AZ1, you are in zone AZ2, so that the database ensures that the followers will not be on the same zone. And then you are fault tolerant not to one node down, but to one availability zone down. And of course, you can run with replication factor 5 if you want more resilience. For example, we have a big retail customer. They run in the US on 3 regions and they want to be resilient in one region is down plus one availability zone elsewhere. So of course it has a cost, more replicas, more network traffic, but they need this kind of resilience.
先ほど一つとして、また4という4をまた立ち上げてみて、状態として戻ったというか、レプリケーションファクターが3なので、1台ノードまでは今耐える形でまた今アクセスしています。で、さっきもちょっとお見せしたのが、Yugabyteではプレイスメントという形でクラウドリージョンかなを意識することができるので、今はちょっとデモで全部が同じ場所にあるという前提ですけれど、仮に、例えばアベイラビリティゾーンを別々にしていると、その、復旧、そのリバランスもそこを考慮してリバランスがされるような形になりますので、そこも一つの、我々の、優位性というか、ユニークなところになっております。
Yeah, let me just put the slides there. So typical deployment in the cloud, you can be single region and then you are resilient to an availability zone. You can also deploy multi-region, also multi-cloud, have some nodes on GCP, some nodes on AWS. Of course, you can also do on-premises. If you have 3 data centers, you deploy among 3 data centers, or if you have 2 data centers, then you don't have a quorum. You see, you need 3 or 5 for replication factor 5. If you have only 2 data centers, then what you will do, you will create a cluster in each data center so that it is resilient to the most common failures, server down, network down. But to protect, in case of the whole data center is down, we can add on top asynchronous replication on top of it. You cannot do something synchronous that ensures that there is no split brain if you have only 2 data centers. You need a quorum, because if the network is down between, you don't know if the other data center is down or just the network. And then if it's the network, each one will think that he is alone and will take writes, and that would not be good. Okay, do you have any questions? Or maybe we just continue and then questions around the drinks. Just mentioning that we have a Slack channel, we have a GitHub. Do not hesitate to be in contact. We are open source to have a community, and my job as a developer advocate is also to talk to users, to people who try it. So do not hesitate. Okay, yeah.
Thank you. I appreciate it. So we can take 2 5-minute breaks. You want to go to the toilet? If you have any questions.
Also, people on Zoom, if they have questions in the chat, maybe.
もし、Zoom で参加の方もご質問があったら、チャットなりに入れていただけるとありがたいです。あるいは QA でも構いませんので、よろしくお願いします。
Just take 2-minute break. The time I have to plug my laptop. So if you want to go to the toilet, just go please.
ちょっと休憩2分をちょっと準備のため2分ほど休憩に入ります。